Silicon, a nondescript gray metal born of flames, is a fascinating material. So intriguing, in fact, a California valley was named for it at the start of the computer boom. Silicon is a semiconductor. Elemental silicon is dark gray in color with a bronze to bluish metallic sheen. Available in various grades of purity, silicon is used in the metallurgical, photovoltaic, and microelectronics industries. Hyperpure crystalline silicon is the starting material for microelectronic applications. It is also the raw material for solar cells. As with microelectronics, it is the semiconductor properties of silicon that are exploited in photovoltaic applications. After oxygen, silicon is the most abundant element in the Earth's crust, making up some 26%, mainly in the form of siliceous minerals or as pure silicon dioxide. The starting material for the production of hyperpure silicon is quartzite, a fine to medium-grained rock that is usually whitish-gray in color and consists almost exclusively of recrystallized silicon dioxide grains. However, it is a long way from quartzite to hyperpure polycrystalline silicon. In order to meet the high-tech requirements of the semiconductor and solar industries, the silicon has to undergo extensive processing and refining. Quartzite is a much sought-after raw material for silicon. The first step in the refining process begins in an electric arc furnace operating at a temperature of 2000 degrees centigrade, where the quartzite is reduced with coke to produce metallurgical-grade silicon. Wacker's polysilicon production starts with metallurgical silicon. The first step in refining this raw material to hyperpure multicrystalline silicon is a fluidized bed reactor. Here, the silicon reacts with gaseous hydrogen chloride at about 350 degrees centigrade to form trichlorosilane, a liquid that boils at 31 degrees centigrade. After extensive distillation steps, the now hyperpure trichlorosilane is reduced by hydrogen at around 1100 degrees centigrade to form silicon again, which is deposited on electrically heated hyperpure silicon rods. Hyperpure elemental silicon grows on the rods in polycrystalline form until an ingot of specified diameter is obtained. This process takes roughly 1 week. The polycrystalline silicon, in short, polysilicon, is now so pure that there is only 1 foreign atom per 10 billion silicon atoms. That corresponds to a 1-cent coin on an area equivalent to 100 football fields. The ingots produced in this way are removed from the reactor and crushed. After the polysilicon has been broken up into chunks and graded, the material undergoes chemical surface refining before it is supplied to the electronics and photovoltaics industries. The sun's energy is captured by solar cells and converted into electricity. Because of ongoing energy policies in numerous industrial countries and escalating energy prices caused by dwindling reserves of fossil fuels, the solar power industry, fueled by photovoltaic technology, is on the verge of a spectacular boom. Over 90% of today's solar cells are made from crystalline silicon. Again, the starting material is polysilicon, which is processed according to various techniques. For multicrystalline solar cells, there are 3 main processing techniques: Bridgman, ribbon growing, and block casting. Once processed and refined, the silicon blocks and crystals are sliced into wafers, approximately 200 microns thick. These undergo further doping steps and are surface treated to reduce light reflection before being processed into finished solar cells. For power generation, usually a number of solar cells are connected together to form a module. As modern solar technology continues to become a more viable, clean, and sustainable source of energy, Wacker is leading the way with silicon-based products and solutions vital to quality and performance, making a difference that will benefit future generations. Wacker, creating tomorrow's solutions.